This video is about Malus's law, but first I just want to review quickly how we draw polarized light. When we draw a ray of light, we usually just draw it as an arrow going in the direction that the light is travelling. But when we talk about light as a wave, we consider the electric fields varying sinusoidally along that ray. And we could draw the electric field lines in here. So if instead of looking side on to this ray of light, we looked face on, the polarization of this light would be in the vertical direction. So this is polarized light that we're talking about here. If instead we considered, again, a ray of light travelling in the same direction, but this time the polarization of the light is in the horizontal direction, and it kind of looks like this. Not a particularly good diagram, but it shows that it's in the horizontal direction instead of the vertical plane. And again, our electric field lines would look like this. And if we were looking end on to this ray of light travelling towards us, it would look like horizontal fields going backwards and forwards, so horizontally polarized. And of course, unpolarized light basically means that it's got all the possible polarizations between vertical and horizontal included in the light. So there you have vertically polarized, horizontally polarized, and unpolarized light, with the side view and the end-on view. Malus's law deals with how much of an incident light, which is polarized. So we start with polarized light, and then it hits a polarizing filter, which is at some angle theta to that incident light. How much of that light gets through? What is the intensity of that light after it passes through the polarizing filter? And you can see here, drawn in red, this polarized light, which is incident on the polarizing filter, which is, in this case, vertically polarized. We know that we will get transmitted light, which is vertically polarized also. And I'll just draw that polarized transmitted light, which will line up with the polarizing filter in black. We can say that in this case of a vertical polarizing filter, only the vertical component of the incoming light will be transmitted. And so we can use this wonderful thing called trigonometry, which I'm sure you've heard of before, where the this side of the triangle here, which is an angle theta to the hypotenuse, this side of the triangle will be the hypotenuse times the cos of that angle. And of course here we're talking about the transmitted light being equal to the incident light, A0, times the cos of the angle between the polarizing filter and that incident light. And I've just added that information there, that the AT is the amplitude of the transmitted light. I'm going to use a little trick here. If you recall back to just a couple of weeks ago, that the intensity of the light is proportional to the square of the amplitude of the light. So if we do a tricky thing here, if we square both sides of this equation, then we have a square of the amplitude on one side and the square of the amplitude on the other side. So we can use this little trick here, that we know the intensity is proportional to the amplitude squared, and we get the transmitted light intensity equals the incident light intensity times the cos of the angle squared. So what does this mean? Well, if you think about it, if the incident light here is lined up with the polarizing filter in black there, then the angle would be 0. And if the angle between them is 0, that means they line up. And so all of the intensity of the incident light is transmitted. So the transmitted intensity is equal to the incident intensity. If, however, the angle is 90 degrees, so they're at right angles to each other, so the direction that's of the polarized light, which is shown in red, is perpendicular to the polarizing filter direction there, then you wouldn't get any transmitted light. It would be 0. Oh, and I really should be careful. I should include some units here. So intensity is the amount of energy, so joules per second per square meter. So this is Malus's law, the relationship between the intensity of the transmitted light and the intensity of the incident light. Often you see Malus's law discussed in context of unpolarized light hitting a polarizing filter, coming through in a certain direction, and then hitting another polarizing filter which is at an angle to the first one. So you've got polarized light coming and hitting it at an angle theta, and then coming out at that angle of the second polarizer. We've just shown, and this is Malus's law, that the transmitted light intensity is equal to the incident light intensity times the square of the cos of the angle between them. Just for completeness, it's also interesting to look at how unpolarized light is affected by a polarizing filter. So it's actually interesting, and you can work out that each of these infinite number of directions here, all of them you can calculate what the vertical component is out of all of those and add them all up, and you end up getting that the stuff that you get out the other side, so the transmitted light in this case is I0, is equal to the unpolarized light intensity divided by 2. So you go from unpolarized light through a polarizing filter, you halve the intensity, and then if you send it through another polarizing filter at an angle, it obeys Malus's law.